Distance learning curricula in machine learning. Introduction to deep learning. Good afternoon and welcome to the machine learning course. This course was developed as a result of the Erasmus Plus project Coding. All you need to learn is internet access and a computer. The course contains a total of 10 topics, and in this topic, we will say something more about the introduction to deep learning. Deep learning is a subset of machine learning that uses artificial neural networks to solve complex problems. Neural networks are essentially algorithms that can recognize patterns in data. The reason why deep learning has become so popular is because it allows machines to learn from large amounts of data and to make accurate predictions or decisions based on that data. Here's a simple analogy to help you understand how deep learning works. Imagine you have a group of people who are trying to identify different types of fruits. You show them pictures of fruits and you ask them to guess which fruit is in each picture. After a while, they start to learn the distinguishing features of each fruit and can make accurate predictions. In the same way, a neural network is trained on a data set of examples, and it learns to identify patterns or features in that data. Once the neural network has been trained, it can make predictions or decisions about new data it hasn't seen before. There are many applications of deep learning, including image recognition, natural language processing, and speech recognition. It's an exciting field that is still evolving, and there's a lot of potential for it to revolutionize the way we solve complex problems. Neural networks are algorithms modeled after the structure of the human brain, consisting of interconnected nodes or neurons that process and transmit information. They're used in machine learning and deep learning to learn from data and make predictions or decisions. By adjusting the strengths of the connections between neurons, neural networks can adapt and improve their performance over time. Essentially, they allow machines to recognize patterns and make decisions based on data, much like how humans learn from experience. Imagine a little creature called the linear unit in the magical world of neural networks. It has one input, sugars, with a weight, W, and a special friend called bias, B. The output, calories, is calculated with a simple formula, y equals w multiply x plus b, which looks like an equation of a line. It's a simple yet powerful way for the neuron to create its output and learn from its connections. Now, let's see how this works in a real-world example with a data set like 80 cereals from www.kaggle.com. Imagine training a single neural model with sugars as the input and calories as the output. After some training, we might find that the bias is B equals 90 and the weight is W equals 2.5. So, if we come across a cereal with 5 grams of sugar per serving, we can estimate its calorie content using one formula. Calories equals 2.5 multiplied 5 plus 90 equals 102.5, just as we expect. It's amazing how this simple linear unit can make predictions based on its learned weights and biases. This can be used for regression problems where the goal is to predict continuous values. Imagine a network of interconnected brain cells, each making decisions based on inputs from the environment. This network is called a neural network, and one of its simplest building blocks is the perceptron. A perceptron has input neurons that receive information, weights that multiply the inputs, and an output neuron that makes a decision based on the weighted sum, passed through a sigmoid function to produce a probability-like output. If the decision probability is above a threshold, the output neuron fires, otherwise it remains silent. With this basic setup, perceptrons can be combined to create more complex networks, capable of learning from data and making decisions, similar to logistic regression. Let's dive into the world of perceptrons and discover their fascinating topology. In a perceptron, the output is calculated by multiplying each input, x1, x2, xn, with its corresponding weight, w1, w2, wn, and summing them all up. This weighted sum is then passed through an activation function denoted by f, which introduces nonlinearity to the output. Finally, a bias term b is added to the weighted sum before passing through the activation function. This process results in the output of the perceptron, which is used to make a decision or prediction. Imagine you're a sailor planning your next sailing trip. You want to know if the weather conditions will be suitable for sailing or not. You decide to use a perceptron to help you with this task. Assuming we have the following inputs. Input 1, wind speed in knots. Input 2, wave height in meters. Input 3, cloud cover in percentage. We have a trained perceptron with the following weights and bias. Weight 1 for wind speed, 0.6. Weight 2 for wave height, minus 0.4. Weight 3 for cloud cover, 0.2. Bias, minus 0.3. With the help of the perceptron model with sigmoid activation function, we can easily predict good weather for sailing based on the input dataset, making it a valuable decision-making tool for sailors. With just a few input values, the model can produce an output that represents the likelihood of good weather for sailing. The power of machine learning and neural networks like the perceptron with sigmoid activation function in predicting and making decisions based on data is truly awe-inspiring. Now, imagine a network of interconnected brain cells working together to make decisions. This network is called a multi-layer perceptron, or MLP for short. It's like a team of specialized neurons working together to solve a problem. The MLP has an input layer that receives information, one or more hidden layers that process the information, and an output layer that produces a prediction or decision. In an MLP, the input layer just receives the raw data, while the hidden layers do the heavy lifting with activation functions that add nonlinearity. It's like a team of superheroes where the input layer sets the stage, and the hidden layers with their activation functions perform the magic to uncover hidden patterns in the data. It's these activation functions that make MLPs powerful learners and allow them to handle complex tasks like image recognition, speech processing, and more. The MLP is trained using a process called backpropagation, where it adjusts the weights between neurons to improve its accuracy over time. It's like a team of neurons working collaboratively to tackle a task and get better with experience. MLPs are widely used for a variety of tasks, from recognizing images to predicting stock prices, and they form the foundation of many advanced neural networks used in machine learning and artificial intelligence. Activation functions are like the secret sauce of neural networks. They determine how inputs are transformed into outputs. Let's take a look at the three most common ones. Sigmoid is like a smooth curve that takes any input and squashes it to a probability value between 0 and 1. It's great for tasks where we want to predict if something belongs to one of two categories, like spam or not spam emails. But watch out for extreme inputs that can make it lose its oomph due to vanishing gradients. Tan, or hyperbolic tangent function, is a bell-shaped curve that can take any input and squeeze it into a value between -1 and 1. It's similar to sigmoid, but it's centered around 0. It's useful when we have data that is symmetric and can have both positive and negative values. Rectified linear unit, or real U, is a do or die type of activation function. It's like a light switch that only lets positive inputs pass through unchanged, but sets negative inputs to 0. It's super efficient and prevents gradient problems, but be careful. It's not bounded and can cause some dead neurons with outputs of 0. In conclusion, deep learning is a rapidly growing field that has revolutionized the way we approach problems in machine learning. In future topics, you will learn about various techniques for training neural networks. To complete this unit, study and review the following online resources. Thank you for attention.